Hi everyone, welcome back. So this time we're going to be talking about a key detail that you might not think about. You are dimensioning for industry. You don't do dimensions just for fun or for theory. There is no theoretical dimensioning here. There's like theoretical physicists, no theoretical dimensioners, no theoretical drafters. You're doing it for someone, for a purpose, to create something that is going to be real. So, all those datums and tolerances that you're going to be establishing, writing down, they establish the allowable variation. Now, keyword here, allowable variation, which means that if you make them too small, not much variation allowed, people are going to have trouble actually making that. Okay? People are going to have trouble making that. So you have to apply the dimensions and tolerances with consideration to the part's use. Does it need a superfine tolerance? Does it need to be perfect? Are there some ways that it can vary and it be okay? Now, you don't always know that from the beginning, but you do your best. Like, for example, if you're creating let's just say a baseball bat, okay? Let's make it a children's baseball bat. There is a whole lot of variation that can happen here, and they can still have fun. It does not need to be perfect. It needs to be baseball bat shaped. And so you're going to see variation. Maybe the handle is slightly angled. Maybe one is slightly longer than the next. It doesn't honestly matter because it's meant for children and it's not meant for anything that's very, very precise. Now, however, if you are building a robot or a part for a robot or a tool that a robot is using to do microsurgery, well, then you can't have a scalpel that, well, oh, my scalpel is actually slightly curved. Sorry about that. That's going to be deadly. So you have to have a much finer precision, a much finer tolerance there. If you're building something for atomic clocks or for things with quantum chemistry or quantum physics, like those quantum computers, then your tolerances have to get finer and finer and finer as we go down. But it's all in consideration to the part's use. What's it going to be used for? Now, if you make a mistake, it's okay, because there are always revisions. This will probably happen as a regular process of when you're making a part or designing a part. People are going to look at it, they're going to send it back to you and say, well, one, I can't do that, or we have to think about this, or did you take into consideration that's being used for X, Y, and Z? So revisions are going to happen. And hopefully those revisions happen before you've sent a product out and gotten manufacturing going. That's why those recalls are so incredibly painful for car manufacturers, because they're wasting a lot of money to retool those vehicles. And it would have been better to make those revisions at the beginning. So be careful in how you apply your tolerances so that hopefully no revisions are necessary, and definitely so that no revisions are necessary down the line. Get them fixed from the beginning and do your best the very first time. Okay, machine capability. Like I said, you're building this for industry. And so there is a range of accuracy depending on the machine quality, the cutting tool, and the machine speed and feed, and the coolant. Depending on what's going on, it's very difficult. I had a friend and he told me that, when you're cutting metal, you should think about it as kind of like you're cutting cheese. It honestly bends and warps the same way as the knife hits it. That edge bends away from it. It doesn't want to get cut at first, and it grabs and pulls and bounces just the same way as the cheese. So be very careful that you realize that when you're asking for accuracy, it's going to take time, it's going to take effort, and it's also going to take talent. People have had to gain the experience in this, and so the harder you make it to make your part, the more expensive it's going to get. So, like I said, smaller tolerance value greatly increase the cost. And if you're not sure, you can find out some guidelines, like machine handbooks for different tools to be used to make your part. Interchangeability. Now, when you're making these tolerances, it should be so that, if you have 10 parts and you have 100, copies of each of those parts, you can pick any of those 100 copies and build your machine without it breaking. If you don't make it so they're interchangeable, well, things are going to fail. So how can you ensure that they're interchangeable? You have to look at your dimensions. You have to make sure that with all the variation in there, there's never a scenario where one part won't fit. Okay, for me, that example, okay, this is not necessarily the best example here, but I have a picture frame and it has 2 circular holes on the back that you use to put the nails in. So you put the nails in the wall and it's all good. I am terrible about measuring those right, and so I always end up messing it up and I'm struggling to get my picture frames on the wall. And that's only with a good 3 parts there, okay? I've moved it one place, it's not that hard. When you have more parts, maybe you have, a plate, and that plate has a couple of bolts coming out of it, and it needs to go into another plate that has a couple of holes in it. That's only 2 parts, that's not bad. And you'll make sure that there's no possible way that these can move side to side or be too big so that it will not fit in this hole every single time. We're going to be going over this as we get towards the end of the class, talking about how there's a buildup in tolerances from feature to feature. And talking about assemblies and how the tolerance in assemblies can be constrained and controlled and taken into account of. So think about this. Be very careful as you're going through it and keep this in mind, okay? Keep it in mind, because there's nothing more frustrating than buying a replacement part that doesn't fit what it's supposed to. Okay, last thing is dimension revisions. I mentioned it earlier. When this happens, you're going to have to update the model geometry, and you're going to have to go through all of your drawings and change those as well. Probably add a note or some sort of symbol to say that things have been changed. So this happens. It's going to happen to you at some point. So make sure that you are ready for it. Make sure you know where all of your geometries are stored, where all of your drawings are stored. That is an entire course in and of itself. Just making sure that those are stored in compliance with current standards and that they are safe, so that people have an issue, they can go back and look at the original drawing and say, well, you know what? This wasn't being made according to the original drawing. That's a big issue. If you don't have your original blueprint and a manufacturer messes up, well, you don't have a blueprint, you can't actually say that they're wrong. Maybe that they built it exactly as you designed it. So you got to make sure that you keep your blueprints. Keep your blueprints so that won't be an issue for you. Okay, that's it for this chapter. I will be doing some application problems, so you can check out those videos too. And I hope this helps you. I'll see you all next time. Bye-bye.